Hi, today we are looking at section 5.8, which deals with related rates. So in this section, we'll be dealing with questions where we're given the rate of change of one quantity and using that to solve for the rate of change of a related quantity. Now, for solving these, it's helpful to draw a diagram and identify all information that we're given. And write down any applicable equations that connect to the information given. We'll then differentiate both sides of the equation with respect to time, or at least in most cases with respect to time, and then solve using given values. So our first example, we're given a rock has flown into a lake. From where the rock made contact with the water, a circular wave is created that spreads outwards at 3 meters per second. I want to know how fast is the area of the circle increasing when the radius is 5 meters. So we know we have a circular wave. We know this would be our radius. It's moving outwards and increasing. We're given the rate at which this is increasing, which we'll call dr dt, is equal to 3 meters per second. And then we're trying to find the rate at which our area is changing, which we'll call dA dt, at when we have a radius of 5. Now, in this case, the only equation that's really applicable is our area of a circle. So our area is pi r squared. Now we'll take the derivative of both sides. So d dt of A equals d dt of pi r squared. So dA over dt is going to be 2 pi r times dr dt. Now we're trying to solve for dA dt at a radius of 5. So that would be 2 times pi times 5 times dr dt, which we're told is 3. So we have 30 pi meters squared per second. Okay, next example. We have a spherical snowball is melting in such a way that its volume is decreasing at a rate of 2 centimeters cubed per minute. At what rate is the radius decreasing when the radius is 4 centimeters? So once again, start by drawing out our situation. So I'll try to draw something that resembles a 3D sphere. We have a radius r. We're given that rate that the volume is decreasing is 2 centimeters cubed per minute. So we'll call that dV dt is equal to, because it's decreasing, we're going to say that's negative 2 centimeters cubed per minute. And we want to know at what rate is the radius decreasing when the radius is 4 centimeters. So we want to know dr dt when our r is 4. So in this case, because we're looking at volume of a sphere, we're going to have to use the volume of a sphere formula. So 4 over 3 pi r cubed. Now in this case, that's the only equation we need. So we're going to take the derivative of both sides of this. So we have d dt of v equals d dt of 4 over 3 pi r cubed. So that gives us our derivative of our volume with respect to time is equal to 4 pi r squared times our derivative of r with respect to time. Now we are solving for this, so we want to move this to the other side, so I divide it over. So we've got dv over dt divided by 4 pi r squared equals dr over dt. Now we want to substitute in the information that we know. So our dv over dt is -2 centimeters cubed. So we've got -2 over 4 pi. Our r is 4 squared equals dr over dt when r is equal to 4. And that's going to give us -1 over 8 pi centimeters per minute. And that'd be the rate at which our radius is decreasing. Okay, next example, we're given a water tank is built in the shape of a cone with a height of 7 meters and a diameter at the top of 6 meters. The tank is being filled at a rate of 2 meters cubed per minute. We want to find the rate at which the water level is rising when the depth is 3 meters. So first thing I would do is draw out a cone. And then we'll label a few things. Now, obviously, this is not to scale because we're told that this total height is 7 meters, while this at the top was 6 meters, which means the top has a radius of 3 meters. Now, I'm just going to draw a line through the center, which represents our overall height. Now, we are looking at what happens when we have a height of 3 meters. And technically, we would have a radius of this circle at that height. Now, we're given our change in volume per minute, so we know that dV over dt is 2.0 meters cubed per minute. And then we're looking at how our height changes. So we're looking at dH over dt when h is equal to 3. Now, in this case, we essentially have two main variables. We have a radius, but that's also related to our height. So what we can do is we can use our ratio of our height and radius for a full cylinder to come up with a radius of and our height at this specific value. So I can say R over H of our full cylinder, so our radius of our full cylinder is 3 over our height of 7 is equal to our radius here, which would be R, over this height of 3. Now rearranging this, that gives us 9 over 7 is equal to R at this height. Now that we've done that, our equation for volume of a cylinder not a cylinder of a cone is similar to that of a cylinder, except for we've got 1/3 in front. So we've got 1/3 pi r squared times height. Now we'll take the derivative of both sides. So we've got d dt of our volume equals d dt of 1/3 pi r squared times our height. So we have dv dt equals 1/3 pi r squared times dh dt. Now we want to rearrange this to get this on its own. So I'd multiply both sides by 3 to get rid of the 1/3. So we have 3 times our derivative of volume with respect to time, divided by pi r squared, equals the rate at which our height is changing. So we have 3 times 2 divided by pi times our radius of that height, which is 9/7, squared is dh/dt at a height of 3. And that gives us 294/81 pi meters per minute. Okay, next example. We have a 32-foot ladder leaning against the side of a building. The base of the ladder starts sliding away from the building at a rate of 4 feet per second. At what rate is the top of the ladder sliding down the wall when the base is 8 feet from the wall? And how fast is the angle of inclination decreasing when the base is 16 feet from the wall? So we'll start by drawing this out. So we have a wall here, we have a floor here, so we have a ladder here. We know the ladder has a length of 32, while our vertical wall, the height at which the ladder is, would be y, and we're going to say that how far away from the wall the ladder is touching the ground is x. Now we're told that this distance is increasing at a rate of 4 feet per second. So you can say dx/dt equals 4 feet per second. And we want to solve for how fast this is coming down. So dy dt, and it's saying when it's 8 feet from the wall, so that's when x is equal to 8. Now what we will do is utilize Pythagoras to link these three sides together. So we have 32 squared equals x squared plus y squared. Now we're going to take the derivative of both sides. So d/dt of 32 squared equals d over dt of x squared plus d over dt of y squared. So that gives us 0 equals 2x dx dt plus 2y dy over dt. So at this point, we want to rearrange to get dy dt on its own. So I'd start by moving this term to the other side. So we've got negative 2x dx dt equals 2y dy dt. Now, what you'll notice is both terms start with a 2, so we can cancel the 2's out. At this point, I would divide this y over, so it gives us negative x over y times dx dt equals dy dt. Now, before we can solve for this, we have to actually figure out what our y value is when x is at that distance. So we will have to solve for that. So we've got 32 squared equals 8 squared plus y squared. So 32 squared minus 8 squared equals y squared. And then we'll take the square root of both sides, plug in our calculators, and we get 30.98 equals our y value. And next we are going to substitute our values in. So we've got negative 8 over 30.98 times dx dt, which is 4, equals our dy dt when x is equal to 4. So we get negative 1.03 feet per second is dy dt when our x is 4. Now, part B is how fast is the angle of inclination decreasing when the base is 16 feet from the wall. So we're just going to redraw what's going on. So we know that our angle of inclination is this angle here. We know this is 32. This is 16. And if we want to solve for this length here at that time, we can say that 32 squared equals 16 squared plus b squared. So 32 squared minus 16 squared equals b squared. So we have 768 equals b squared. We take the square root of both sides and change it to a mixed radical. We get 16 root 3 equals b. So we know this side here is 16 root 3. Now this will still stay as our x value. And we still know that our dx over dt is 4 feet per second. And we are solving for d theta dt when x is equal to 16. So what we want to do is utilize a trig function that involves the side that we're given and that has a rate of change. So that means we want to utilize this side here. Now, because we know this side is also changing, I would utilize this side. So if we're using this side and this side, that's our adjacent and our hypotenuse. So we can say that cos theta is our adjacent over hypotenuse. So that gives us our cos theta is currently our adjacent, which is x, over our hypotenuse, which is 32. And this would be true for any location of our ladder. Now, before we go further and take the derivative, we also should probably figure out what our starting angle is when we are 16 feet from the wall. So we can use our cos, rearrange it, so we've got theta is equal to arc cos of 16 over 32, which is pi over 3. So we'll need that later on, most likely. We'll now take the derivative of both sides. So we have d dt of cos theta equals d dt of x over 32. Now, we will take the derivative of this, so that gives us negative sine theta d theta dt equals 1 over 32 times dx over dt. Now we're trying to solve for this part here, so we divide both sides by the negative sine theta. So our rate at which theta is changing with respect to time is 1 over negative 32 sine theta dx dt. Now, if we're looking d theta dt at an x is equal to 16, then we have 1 over negative 32 times sine of our angle of pi over 3 times dx dt, which we know is 4, and that gives us a d theta over dt of negative 1 over 4 root 3 radians per second. Okay, on to another example. A student starts walking south at a speed of 1.5 meters per second. At the same time, and from the same starting point, another student starts walking east at 2 meters per second. At what rate is the distance between them increasing at a time of 1 minute? So I'll start by drawing things out. So we do have essentially one person walking this way while we have another walking this way. So we'll call that X and Y. And we eventually want to know what the distance between them is from here to here. And we want to know what is a time of 1 minute. Now, 1 minute is 60 seconds, so we can get how far apart these are at that time. Because if we go 60 times 1.5, we know that that's going to be 90 meters. And if we do 60 times 2, that gives us 120 meters. Now we want to know this side here. So we would use Pythagoras. So we've got, if we call that X and Y, I'll just call this Z. So we know Z squared equals X squared plus Y squared. So Z squared is 120 squared plus 90 squared. And that gives us a length of 150. And then at this point, we'll once again take this formula. So we've got Z squared equals X squared plus Y squared. And we might as well write out the derivatives that we technically already know. So walking south at 1.5. So that was our y. So we know our dy dt is 1.5 meters per second. And how much we're east is 2 meters per second. That's our x. So we know dx dt is 2 meters per second. Now we're going to take the derivative of this. So we have d dt of z squared equals d dt of x squared plus y squared. So we have 2z dz over dt equals 2x dx over dt plus 2y dy over dt. Now, one thing that you'll notice is every term has a 2 in it, so we'll go through and cancel those out. And we essentially now just want to get dz over dt on its own. So we've got dz over dt is equal to x times dx dt plus y times dy dt over z. So we've got dz dt when we're looking at a time of 1 minute. A time is 60 seconds. So that would be our x, which at that point is 120, times our dx dt, which was 2, plus our y at that location, which is 90, times dy dt, which was 1.5, over our z at that time, which was 150. So if the rate at which the distance between them is increasing at that time is 2.5 meters per second.